Yes. So we discussed that that there is a wonderful theory of Riemann-Hilbert problems, and that theory has a kind of abstract side that leads us to consider questions of existence and uniqueness of solutions of Riemann-Hilbert problems, and involves ingredients of Fredholm theory from functional analysis. There's also a small norm aspect of the theory. So we connect the Riemann-Hilbert problem to a certain integral equation, and under some circumstances, we don't really need all the power of the Fredholm theory, as long as we can ensure that the operator involved is a sufficiently small perturbation of the identity. Then there's a nice crank that we can turn to generate an approximate solution by summing some kind of Neumann series. And I also remarked that most problems don't have that character, but sometimes if there's a parameter in your problem, then there's a way that you can deform your Riemann-Hilbert problem and change it into an equivalent one by some change of variables. And once you have arrived at the equivalent problem, if you've done your work right, you can check that what you have in your hands is a small norm problem. And so I would like to, in this lecture and the next one, I would like to show two illustrations of this technique, which is the Dave-Joe steepest descent technique. It goes back to Dave and Joe in the 1990s, originally in their work on the Painlevé-2 equation, as it happens, but a different asymptotic problem than the one that we'll consider tomorrow. So the first application that we need to consider is this. Riemann-Hilbert problem that's behind orthogonal polynomials. So let's just remember what that problem is. So this is the problem that was found by Fokas, Itz, and Kitaev on some. They were studying some interesting problem in quantum gravity, and somehow this Riemann-Hilbert problem appears in the middle of their paper in some way that turns out to have a much more far-reaching implication, I think, than they thought when they wrote the paper. But anyway, so n greater than or equal to 0 is an integer, and we're looking for a matrix a n of z. This is not a power, it's just an index, okay? 2 by 2 matrix that should be analytic except on the real line in the complex plane. The analytic function should extend continuously to the real line from the two half planes, but the boundary values don't match. And so if we use a plus to be in the boundary value from the upper half plane and a minus to be the boundary value from the lower half plane at some point x on the real line, then the boundary values are meant to be connected by this jump condition that involves a function w of x defined on the real line. And then we demand that the matrix a n of z should be normalized as z tends to infinity, so that if I multiply on the right by this diagonal matrix, okay, z to the minus n, z to the n, and I take the limit z to infinity, then I should get the identity matrix, and it shouldn't matter which direction I take the limit in the complex plane. So that's the Riemann-Hilbert problem of Fokas, Itz, and Kitaev. And then we may recall that the solution of this problem can be written in terms of the orthogonal polynomials with respect to this inner product built from the weight function w that appeared in the 1-2 entry of that jump condition matrix. So here we are orthogonalizing f and g against this w measure on the real line. That's the inner product. So in summary, the solution of the Riemann-Hilbert problem for n greater than 0 had this form. This element here, that's the monic normalized polynomial of degree n in the system. So generally speaking, the orthogonal polynomials have a leading coefficient gamma sub n, which is positive, but if we divide that out, we start with x to the n, then that's what pi sub n of x is. Okay, so this is basically the nth orthogonal polynomial here. And here, this is the n minus first, and there's some other constant that shows up there. And then the things that are in the second column are just the Cauchy transforms of the things in the first column, but multiplied by the weight function w. Okay. So so the Cauchy integral, as I'll remind you, is this formula down here. That's what's standing in the second column. So that's the solution of the problem. It's really an explicit solution in some way, except that we should remember that in order to build the polynomial pi n, we have to do something like this Gram-Schmidt algorithm. So we have to start with the constant function and normalize it, then take the linear monomials, subtract the constant to get it to be orthogonal to the constant, renormalize, and repeat over and over again until we get to degree n. And we can write that procedure as like a ratio of some Hankel determinants or something, but these determinants are growing in size as n goes to infinity. And if we would like to understand something like how does pi n of z behave when n is large, it's not so useful to have this formula. It's just not the most useful thing to know. So on the other hand, if we can go back to the conditions of the Riemann-Hilbert problem, then you see that the only place that n shows up is really right here, okay? So I'm actually going to solve a slightly different problem because I'm going to make the weight function depend on n as well. So then it will show up in two places, here and here, but completely explicitly. And then we may think maybe that's an easier problem to analyze, and if we can solve it and take out the 1, entry of the matrix, then we will have this in our hands, or some approximation of it anyway, and that's what's behind our approach. So we're going to assume, to be in this setting that's handy in random matrix theory, we're going to assume that the weight function has the form e to the minus n times v of x, and n here, that's meant to be the dimension of my random matrix, which is not the same thing as the matrix an. That's a 2x2 matrix all the time, but in random matrix theory, I'd like to consider n by n matrices, and I can express certain statistics of the eigenvalues of those matrices in terms of the 2x2 matrix, A superscript n of z. So now you see the weight has this n in it here, and the degree of the polynomials that will be interesting to us is also going to be n. Those things will be related. Okay, so we need this reproducing kernel of random matrix theory. That can be written in terms of the first column entries of this matrix here. And so we're going to be interested in how this A superscript n of z behaves as the matrix size for random matrices goes to infinity. But this is always a 2x2 matrix. It just has the parameter capital N, both in the normalization condition and in this function w of x. So as we said, this is not a good problem to consider from the point of view of the Gram-Schmidt procedure because that has increasing complexity, but the n is an explicit parameter in the Riemann-Hilbert problem. So we will apply the Dave-Joe method, and the procedure is going to consist of just a finite sequence of completely systematic transformations of the matrix unknown. So we'll start with an of z, and with a certain goal in mind that I will explain, we will try to transform it into B and then into C. And this is a good place to rest for a moment, at which point we will do some deformation of the Riemann-Hilbert problem by moving contours in the complex plane to change C into D. So this step here involves moving some contours in the complex plane, and it's that step that's some kind of Riemann-Hilbert analog of the method of steepest descent for evaluating contour integrals. Okay? So that's that step. And finally, we will have this one, and we will make some explicit model for this matrix D sub n of z, and compare the model to this matrix. And that will lead us to another Riemann-Hilbert problem for an unknown called E, n of z, which I like to think E is meaning error, okay? So this En of z is the error associated with our modeling of this D, and it satisfies a Riemann-Hilbert problem that we will show has this small norm character when n is large. And that means we can solve for this En by Neumann series, and since we know what that is, and we can invert all of these arrows, we will have information about this An, okay? That's how we're going to get our asymptotic formula for An. Yes?
The rule is n tends to infinity.
Correct. That's the same as thinking of large random matrices, many eigenvalues. So for instance, there's a famous random matrix ensemble called the Gaussian unitary ensemble, GUE, and that one takes the V that's over here. Oops, let's go back. It takes the V to just be x squared, okay? And so then in that setting, it was found a long time ago that probably by Wigner, that the eigenvalues of a random matrix from that ensemble, they tend to sit in some interval of the real line, and they're distributed as if they're distributed with some kind of probability law that's like the graph of which is like a semicircle. It's called the Wigner semicircle law. So anyway, we will see that. We'll derive that soon. But
Okay, so I'm trying to ask. So usually, for example, we care about large time asymptotic. That's totally different.
So it seems different, but actually, so this is a matrix element in our jump matrix for the Riemann-Hilbert problem, and you'll notice that the n, the large parameter, is just in the exponent there. And if you do large time asymptotics for PDE, integrable PDE, then it's the same story, right? You just have you have e to the t times something, some phase, right?
In this case, there's no, we don't need to discuss stationary point.
In this case, well, it's every problem is different. That's right. So, yes. That's not the plan, but but we may discuss but yeah. So in some problems, that would be the interesting question, like what are the critical points of this V? But it turns out that in this problem, for some reason that I'll explain shortly, there's another step that has to happen before we would even think about those sort of things, and then it leads us in a different direction. Yeah. Okay. So really. Yeah, so the most obvious difference between the Riemann-Hilbert problem that we are looking at for this AN and a small norm problem lies in the form of the normalization condition. So that one so instead of saying that A sub n goes to the identity as z goes to infinity for a given n, we are asking that A sub n times z to the n sigma 3, minus n sigma 3, goes to the identity as z goes to infinity. And that's a bit of a problem. It doesn't look at all like the identity matrix, at least near infinity. So you could imagine trying to fix the problem by cooking up some kind of a scalar function, g of z, that behaves like log z at infinity. Because then, if you were to transform a into b by this formula, so an is e to the minus n g sigma 3, if g looks like log z, then e to the minus ng looks like z to the minus n sigma 3. And that product then is something that would tend to the identity matrix as z goes to infinity. So this is the game, okay? So if you could find such a function, then you would pick up the right normalization condition on the B matrix anyway. So at this point, it's important when you do that, that when you pick this g to behave like log z, you don't want to mess up, in some sense, other properties that this matrix A is supposed to have. So, for instance, you don't want to mess around with the analyticity in the upper and lower half planes or the continuity of the boundary values taken by the matrix on the real line. So, that's what stops you from just taking g of z exactly to be log z, because if you did that, then e to the g would be z. And so you would have here z to the minus n, z to the n, and that z to the minus n puts a pole of order n into the matrix B at the origin. So that would be no good, okay? So that's too simple of a thing to do, and it would mess up the continuity of the boundary values. So we still want g to be analytic in the upper and lower half plane. We want it to look like log z at infinity, but we got to be smarter than just to set it equal to log z. So one idea that you might have is that you could kind of smear the pole out, the pole we just discussed at the origin of order n. You could smear it out in this way. So suppose that psi is just a real valued function on the real line. It's Hilbert continuous and it's integrable. And suppose that its total integral is equal to 1, okay? So then you could express g as kind of a log transform like this. So then you see, like, if this psi was a delta function, right, then we would just recover exactly log z, and that's the thing that I was saying is not a good idea, okay? But if this psi is some other function that has integral equal to 1, then this is some kind of a distribution of the delta into some interval on the support of this psi, and then this has got better boundary values, okay? So that's the idea. So if you write this kind of formula, then g of z is an analytic function of z, except on the real line. it takes continuous boundary values on the real line from the upper and the lower half planes. And if you expand for large z, you can pull out log z from the integral like this, and what's left over as a coefficient is this number, which is 1 plus small. Okay? So that's telling you that you get exactly the desired behavior at infinity. And so, so what we managed to do is to sort of smear out the pole by replacing this point mass by some absolutely continuous measure. Okay? That's the thought. So, okay, so far so good. So consequently, if you take such a g function, then this e to the minus n g sigma 3 really looks like z to the minus n sigma 3 as z goes to infinity, and so B will tend to the identity. And that means that this matrix B will solve this equivalent Riemann-Hilbert problem 2. So now we're looking for the 2 by 2 matrix Bn that's analytic except on the real line. It takes continuous boundary values from above and below that are related by this condition. So here what's happened is that we've had to bring this g function into the jump condition because the matrix A did not have this g. We just had 1, 0, e to the minus nv1. But what happens when we conjugate by that g is that it's got different boundary values from the upper and the lower half planes. And that means that it appears in the jump matrix. On the diagonal, we pick up e to the minus n, the difference of the boundary values, or e to the n, the difference of the boundary values. And on the off diagonal, we pull in the sum of the boundary values. That's how it works when we write out the jump condition for B. Okay, so now that's appearing, and that might be annoying because we haven't said exactly what this thing is yet, but anyway, it's showing up in the jump conditions. So that finally the matrix Bn should be normalized at infinity to be the identity. That's the way we pick this G. So I think you might look at this and decide that that's bad because I don't know now anything about this jump matrix like I used to. Or you might have a more positive point of view and you might say, well, what this is doing is it's giving me some freedom because if I pick this G function the right way, these plus and minus things will help me out. It's going to somehow make this matrix into something better that I could do analysis on. Okay, so it's a freedom that we should somehow not disregard. Okay, so anyway, so now how do we choose it? So that's going to involve some business from logarithmic potential theory. So we're faced with the question: how should we choose the function psi that is in our formula for G to our advantage in considering the limit n to infinity? So to begin to think about it, we should write out what these g plus minus g minus that shows up on the diagonal and v minus g plus minus g minus that's on the off diagonal, what are those in terms of psi? So to do that, the formula for g involved the logarithm under the integral, so we should take boundary values of the principal branch of the logarithm. So if you fix a y value and you let x go to the real line from above and below, like this, then you either get the log of the absolute value if x is bigger than y, or the same thing but with a plus or minus I pi if x is less than y, right? That's a simple thing to calculate. And so that means that the boundary values g plus or minus of x can be explicitly expressed in terms of this function psi in this way. And so that means that the exponents that are showing up in the jump matrix, well, one of them is g plus minus g minus, and that one we might write as I times a function theta of x, which is exactly just 2 pi times the integral from x to infinity of psi. So it's some kind of an integral antiderivative of this psi. And on the other hand, on the off diagonal, we had v minus g plus minus g minus. Well, adding these two things together will cancel this term, so we just have minus 2 times the integral of log x minus y absolute value psi y dy plus the v of x, okay, which is just this part. So now we have expressed those quantities in terms of psi. And okay, so it turns out that the right-hand side of the off-diagonal entry, that's this quantity here, that can be viewed in a nice way. It's actually the derivative of a functional, okay? It's like the variational derivative or a Frechet derivative of a certain functional of psi, which is called the energy, and it's written like this, okay? So I'm going to say a little bit more about it later, but the thing that you should think about here is that this psi is like a distribution of electric charge, okay? And so, in the plane. And this quantity over here, that's the Green's function for the, for a Coulomb repulsion, okay? So this term here is measuring how much these charges don't want to be close to each other, okay? That's like a penalty energy for a charge to be close to itself. And this term over here, this is like some potential, okay? And so depending on the shape of this potential, this gives a contribution to the energy, depending on where these charges are distributed in relation to the minima and maxima of this V. So this is like the potential energy of some external field, V of x, okay? And so just, anyway, that's an interpretation of this E of psi, but the point is that if you go in here and you replace psi with psi plus epsilon times some test function, and you kind of expand formally for small epsilon, the first term is just E of psi, and the second term is epsilon times the integral of on the real line of something times this test function eta plus smaller terms. And this U that's showing up by definition, that's what we mean by delta E delta psi. And the point is that's exactly this expression here, okay? That's exactly that expression. So there's some kind of physical interpretation creeping into this problem, whether we like it or not. So let us now suppose that this function psi is non-negative in addition to being normalized to have unit mass, okay? So that makes this psi into a probability measure, I guess if we multiply by the differential dx. So we have a probability measure now. So physically, we've got the Coulomb energy of a distribution of unit positive electric charge that's confined to the real line, but the universe is two-dimensional, and that's why the Green's function is the Laplace, coming from the log of Green's function for Laplace equation in 2D, okay? And the charges are influenced by mutual repulsion, which is the double integral term with the log, and they're also trapped in some external field V, okay? So by definition, the equilibrium measure is just the probability measure, psi dx, that minimizes the energy. And it turns out that under some very general conditions, it exists and it's unique. The V just has to grow fast enough at infinity. The potential has to grow fast enough at infinity to confine the charges. And so this is some very general arguments that lead to this statement, but the definitive statement is the Gauss-Frossman theorem. Okay. So there's an equilibrium measure that minimizes this energy. So that equilibrium measure, you can characterize it by some variational conditions. So there's a constant L, a real constant L, so that when psi is the density of the equilibrium measure, we have in the support of psi that the variational derivative of the energy is exactly constant, this number L. Whereas outside the support, the variational derivative exceeds that constant L. And the way that you get these variational conditions is just you enforce the constraint of unit mass on the function of psi using just Lagrange multipliers from calculus. So you just consider the augmented functional energy minus Lagrange multiplier times mass minus 1. And so then you attempt to minimize this thing simultaneously with respect to psi and L. Okay, and the psi has to satisfy this constraint here. Because we're assuming that we have a probability measure, the constraint that the mass is 1 will be built in automatically from taking the derivative with respect to L here.
So L is determined by V.
L will be determined by V, that's correct. And so will psi, actually. Okay. So suppose that psi 0, L 0 is a minimizer of this augmented functional. So then since f shouldn't become any smaller by varying the multiplier close to L naught for fixed psi, then it's necessary that the derivative with respect to L should be 0 at the minimum point, and that's just the constraint mass equals 1. And similarly, the f shouldn't be made any smaller by varying the density of the equilibrium measure near its minimizing value at the fixed multiplier. So here we can vary this by just taking, as we did before, psi 0 plus eta times epsilon times test function. And this thing here, we should think of it as a test function that has compact support near this point x naught in the real line. So then the way that this modified functional responds to such a perturbation is just by the usual expansion like this. So we have the variational derivative showing up at order epsilon like that. And then since the variational derivative of the mass with respect to psi is exactly 1, that means that the df d psi is exactly de d psi minus L. That's what's standing here. Okay. So in this expansion, what we're going to do is evaluate everywhere the variational derivative at psi 0, L 0. Okay. So now there's kind of two cases. So the first case is that if this point x naught is in the support of our density, so it's a point where psi 0 of x is positive, okay? So then the inequality that psi of x should be greater than or equal to 0, well, psi is the original value plus this test function perturbation, and that's going to hold for all x close to x naught if epsilon is small enough, regardless of the size of this thing, okay? So the point is that this is already positive, so you're not going to get something negative by adding a little bit, okay? So the linear term in the expansion of f can then be made to have either a positive or a negative sign just by choosing the sign of this test function eta, unless the variational derivative of f with respect to psi is 0 at the point x naught. So if x naught is in the support, I need this to hold true, and this gives us the equilibrium condition that we had in our, well, let's see what 10 is. Let's go remind ourselves what that is. That gives us this condition here. So x is a point in the support. And remember that de d psi minus L is just the variational derivative of that modified functional f. Okay. On the other hand, if x naught is outside the support, okay. If x naught is a point outside the support, so then we have that psi of x is eta. Well, the psi 0 term is gone, so we have epsilon times eta for all x near x naught. And so now we need this to be positive. So the eta, the test function, it has to be positive when we multiply by epsilon. That's got to be true. But such a perturbation can only act to increase the functional f, so it's necessary that this inequality holds true. And this is the other condition, the one with the strict inequality. That's the condition that holds outside the support. Okay, so the variational conditions just come from assuming you have a minimizer and just considering the fluctuations nearby. That gives you those variational conditions. Okay, so we'll use those. But some simple properties of the potential, they can affect the equilibrium measure. So here's just two things, kind of quick, I guess. So the first is suppose that v grows at infinity. So v of x is growing faster than log of x as x goes to infinity. So then the corresponding equilibrium measure, psi x dx, has compact support. And this is pretty easy to get because the specified growth condition on v, that guarantees that the variational derivative of our energy is increasing as x goes to infinity, because that thing had two terms in it. There was a log transform, which grows like a log, and there was the v function, which grows faster than a log. So this goes to plus infinity. Now suppose that xn is an unbounded sequence of points in the support of the equilibrium measure. So then there's some constant L, that's the Lagrange multiplier, so that de d psi is exactly equal to L for all n, because those are points in the support. These xn's are points in the support. But the left-hand side over here, this has got the v function in it, so it tends to plus infinity as n increases because these points are going to infinity. But this is a constant. So that's a contradiction, and there can be no unbounded sequence in the support of this function psi x. So since the support, by definition, it's the closure of the set where psi is positive, then it's a compact set. It's both closed and bounded. Okay? So we have compact support with just logarithmic, a little more than logarithmic growth of the potential. We're going to usually take v to be a polynomial, so there's really no problem there. Okay, so next, another simple thing. So if you think about this as like a problem with an electrostatic potential v, okay? If v double prime is positive, that means that you have just a single well potential, right? And it's perfectly reasonable that in such a case you would expect that the charges should all be in a single lump, okay? Somehow there shouldn't be any gaps in the support of the equilibrium measure. And that's an easy thing to prove. So suppose that v satisfies the growth condition and is also strictly convex. So then the equilibrium measure is supported on a single interval alpha beta, okay? So to do that, to show this, it's sufficient to rule out gaps in the support. So suppose there was a gap in the support. So then if we take this variational derivative of the modified functional, so d deep psi minus L, okay, this function has to have a graph that looks like this picture. There we go. Okay, it looks like this picture, right? Because f should be satisfy the equilibrium condition in the support, so it should be 0 out there. But in the support, but in the gap of the support, it should be positive. That's inequality 11. So this is 10 and this is 11 in our formulas. Okay. So anyway, so now if we're in this gap, we can differentiate twice under the integral sign and get a formula for f double prime. So that's the second derivative of this d deep psi, and in differentiating 2 times that logarithm in the kernel, we're going to get x minus y squared in the denominator with a factor of 2, and then plus v double prime. So this should hold in the gap. So if v is a convex function, this thing is strictly positive. This thing is obviously strictly positive because psi is a positive function and there's a square here. So this has got to be positive, okay? On the other hand, look at the graph. Here is a point, I'm just making a sketch, of course, but this is a point where obviously f double prime has to be negative, okay? It's just a consequence of the fact that f is positive in the interior here and 0 on the outside. So it's a contradiction, okay? By calculus. Okay, good. So no gaps allowed in the support. Okay. So how do we find the equilibrium measure? Well, what we're going to do is we're going to go a little bit indirectly. We're going to find g prime instead of psi. So for z in the complex plane away from the real line, we differentiate this logarithmic transform formula for g. So we have to differentiate the kernel, which was log z minus x, and then we're going to pick up this thing here. And you'll notice that what this is just a multiple minus 2 pi I of the Cauchy transform of this psi on the real line, okay? So g prime is proportional to the Cauchy transform of psi. That means that if you could figure out what g prime is, then you will know what psi is, because you can apply the Plamelge formula here to subtract the boundary values, and that's going to give you psi in terms of the boundary values of g prime, just from this formula up here. Okay, so now if we differentiate the condition 7, I forgot what that was, maybe I'll try to remember. Okay, so that's the formula for the off-diagonal exponent. We're going to differentiate this one. Okay, so differentiation of that off-diagonal exponent and using the variational condition that holds true in the support says that g prime plus g prime minus is the same thing as v prime of x in the support, because we've killed this Lagrange multiplier L by differentiation. It's a constant, so it disappears. On the other hand, from this one up here, right, we see that as long as we're not in the support, this psi is 0, and the difference of the boundary values of g prime has to vanish, okay? So in terms of points x on the real line, either you're in the support or you're not, and that means that either we're being given the sum of the boundary values of g prime in terms of something we know, or we're being given the difference of the boundary values of g prime in terms of something we know, okay? So it's close to sort of a Plamelge type situation where we could reconstruct g prime from these right-hand sides. The trouble is we don't know what the support is, but we have some other information. We also see by differentiation, since g behaves like a log at infinity, g prime is 1 over z plus smaller terms as z goes to infinity. So what we're going to think of is those last two equations giving us alternately the sum and the difference of the boundary values of g prime together with this equation here. I want to think of those as equations to be solved for g prime that's analytic in the complex plane, take away the real line, and once we know g prime, then we'll just get the equilibrium measure by the Plamelge formula. Okay, so the support, unfortunately, is an unknown interval, alpha, beta, but we're going to see how to determine that interval systematically now. So we can make the two types of formulas, the sum of the boundary values and the difference of the boundary values, we can make those two look more the same by a certain trick that I will call the square root trick. Okay, so we're going to consider a function r of z. R is just meant to stand for root, okay, square root. So R of z is like this, some kind of square root of this quadratic z minus alpha, z minus beta. Those are, and alpha, beta, those are the unknown endpoints of our support interval. However, that's not enough to specify this function uniquely. We want it also to be analytic in the complex plane, take away this kind of branch cut, alpha, beta. We'll make that the branch cut for our complex valued function R of z. And then we want R of z to behave like z as z goes to infinity. So actually, in terms of the principal branches of power functions, we can write R of z in this form, the product z minus alpha to the half, z minus beta to the half, but we should be a little bit careful. This is not cavalier to write it this way because, for instance, it's not the same thing to express R in this way. This is not a valid formula for R of z. Here we are multiplying first and then taking the square root. Here we are taking the square roots first and then multiplying. They're not the same, and it's a little exercise in complex variables to think about why that's the case. But anyway, this is our formula here, okay? So that's the square root trick. So what are the properties of this square root? Well, so first of all, if we're not in the support alpha beta, then R plus and R minus are the same thing. The boundary values from the upper and lower half plane agree. The only branch cut is this alpha beta. But in the branch cut, it's a square root, and there are only two answers for the square root, and they're opposites of each other, right? That's what happens when you take square roots. So on the branch cut, R plus is not equal to R minus, it's equal to minus R minus, okay? So now what we're going to do, we're going to use these facts, the fact that there's no minus sign here and there is a minus sign here, to change plus into minus exactly in the support. That's our goal. So we're going to make a change of variables. Instead of looking for g prime, we're going to look for g prime divided by r, and we'll call that h of z. So then h of z is going to be an analytic function in the complex plane, take away the real line, and using these facts here, along with the two jump conditions for g, we see that the boundary values are always going to be a difference now. So h plus minus h minus always is equal to either this or that, depending on whether you're inside the support or outside the support, okay? Anyway, so this is the plus boundary value of this function r, which is a positive imaginary quantity as it happens. Okay, so now, so from the asymptotic condition on g prime, which g prime should be like 1 over z squared, and the fact that r of z is like z at infinity, then we see that this h has to be z to the minus 2 plus big O of z to the minus 3 as z tends to infinity. So this is a condition on h now, and I have the difference of the boundary values as something given at every point on the real line, and this h goes to 0 for sure because z to the minus 2 decays at infinity. That means we can write a formula for what h is by the Flamel's formula again. So h of z has to be exactly 1 over 2 pi I integral alpha to beta of this thing, Cauchy integral, right? So x divided by x minus z, so that's the Cauchy integral of v prime over r plus, okay, in the interval alpha beta. So that's what h has to be. But anyway, if you take this and you just expand it out, you see that the leading term is some constant divided by z, and then there's smaller terms after that. That means that for this formula to satisfy this condition, I have to kill the 1 over z term, and I have to get the right coefficient on the 1 over z squared term in the expansion for large z. That's what we have to do. So that's it. So we expand out this h, and you see here's the 1 over z term, it's this thing, and here's the 1 over z squared term plus smaller, okay? So in order to get h to be like 1 over z squared at infinity, I have to kill this term, and I have to make this one equal the right number. So that's what this formula says. So now we count. We have 2 equations here, and there are exactly 2 unknowns in our problem, alpha and beta, okay? So 2 equations and 2 unknowns, there's a chance we should be able to determine alpha and beta, the support endpoints, from these 2 formulas, okay? So, so let me now explain some further tricks. So if the v here is like an entire function, okay, so instead of being just the convex function on the real line, you could extend it into the complex plane as an entire function. So then you can compute these integrals exactly, and you'll see how it works. So this is how it goes. So suppose start out by writing this condition, condition 18 is the formula for h. So what I did is I took 1 over 2 pi I times integral, and I just divided by 2 and wrote it 2 times. Okay, that's not so complicated. But now, in the second term, okay, I'm going to remember that in the support alpha beta, r plus is minus of r minus. So I put minus r minus there. Okay? And now the thing is, if you think about what these look like, so if this v is an analytic function, it's like I'm integrating some integrand along the plus side of the branch cut of this function r from alpha to beta. And then minus, I'm starting at beta and coming back to alpha on the other side of the same branch cut. Okay? So that's how we have to think about it. So now we do some tricks. So here's the idea. So we first integrate alpha to beta on the plus side, and then we add in beta back to alpha on the minus side. That's what we start with. But our v is analytic now. It's entire. And the only other singularity of our integrand is a pole, a simple pole at the point x equals z. Okay? So we will first use the generalized Cauchy integral theorem to expand this into a little loop like that. So we have this loop. And now we want to make the loop even bigger, and we can do that, but we have to pay the price of a little residue at the point z, like that. So now we've written everything in terms of this integral, which is a residue calculation. It's a simple pole at x equals z, and this big loop over here, this large loop, okay? So here's the residue part. This is evaluating the residue at x equals z. And this is the part left over, the integral over L. But again, v is an entire function, so there's no singularities of the integrand at all outside of this loop L, so we can compute this integral also by residues. Now the residue is at the point at infinity, okay? So that's the formula we have here. This is the point at infinity evaluated now. And so to do that, what we need is the expansion, the Laurent series of this function for large W. Okay, so here it's useful to expand the Cauchy kernel like this for large W. That's straightforward. And 1 over r is a little bit trickier, but r is the square root of this quadratic. And so it's systematic to write down as many terms as you like. And the coefficients just involve the alpha and the beta, which are the interval endpoints, the support interval endpoints. So combining this one and that one, and if we know the expansion of v prime at infinity, then we can pull out this residue in a simple and straightforward way. So here's the first example is the one I mentioned earlier. V of x is equal to x squared. That's the one that shows up in the GUE ensemble. So the function vx equals x squared is strictly convex, and it's thankfully entire, so we will use this method. So then v prime over r times w minus z has this expansion, and all we need really is the 2 over w term to do the calculation, because the residue at infinity is just 2. So that means that h of z is exactly z over r minus 1. What could be simpler than that? And if we expand that function at z equals infinity, then h of z is 1 over 2z alpha plus beta plus 1 over 8z squared times this number plus smaller. And so the conditions on our 2 endpoints are that this is 0, and that this one is equal to the right constant. So alpha plus beta is 0, and this quantity is equal to 8. Those are our conditions. So now you say, okay, I need to solve that. Obviously, alpha and beta are opposites of each other. And then you put it in here, and then this is a quadratic equation on, say, beta, okay? So beta is the square root of 2. You can check, okay? So anyway, so now alpha and beta are opposite values, plus or minus root 2, and the endpoints are known. So now we can get the equilibrium measure by using the relation between g prime and h, which is this explicit formula. H is this function, and then all I have to do is take the difference of the boundary values of g prime using the Plamelge formula. So since z, this part has no jump on the real line, and this one, the boundary values have the jump of plus or minus I square root of 2 minus x squared in the support interval. So then the function of psi is just this thing supported in the interval minus root 2 to root 2, and that is the semicircle law from Wigner's random matrix theory, if you like. Okay? It's also the distribution of the zeros of the Hermite polynomials. It shows up all over the place. Okay. So anyway, so that's the simplest case. That's x squared. But, it's not just that. Okay. We can also do x to the 4. So in this case, the expansion is this crazy thing, but we peel off the residue that we need. That's this quantity, okay? And so therefore, h of z is this expression. Now that needs to be expanded for large z, and here's the expansion up to order z to the minus 3. So this has to be 0, and this quantity in parentheses has to equal 64, okay? So, right? All right, so now this quantity that has to equal, that has to vanish, it actually factors. There's an alpha plus beta factor and something else. And it turns out that this one has no real roots. So alpha and beta are real numbers. That means alpha must be minus beta over here. And consequently, I take alpha and beta opposites, I put them into this equation, and beta to the 4, beta being a positive number, beta to the 4 is 4/3. So that tells me exactly what the support interval is in this case. And then finally, I have the formula for G prime. That's R times H, and H was this expression. H was the expression back on the previous slide, which over here. H is this thing, and I know what those coefficients are now. So this is what R times H is. And finally, by subtracting the boundary values here, the density is this expression. So again, there's this kind of square root type term, like semicircle law term, but there's an additional quadratic factor multiplying in front like that. So it's interesting to compare the two. So this is the equilibrium measured density for the quadratic potential. That's that one. And this is the one for x to the 4. So it's interesting, even though the potential, the quartic potential is a single well potential, somehow it's kind of flat at the bottom, and that allows the charges to kind of, they try to separate from each other. They can't completely separate because the potential is convex, but they still form kind of two lobes, right? Like that. There's a bunch of charge over here, a bunch over here, and there's slightly less in the middle. Okay? All right. So I think now, exercise, do it for x to the 6, for example, right? Okay, so at this point onward, we're going to assume that this function psi that we use to construct G is exactly the density of the equilibrium measure associated to V. So then in terms of the quantities that we defined earlier, the jump condition for B can be written in this form. So here we have e to the minus in theta. That was like the integral, the antiderivative of psi. And then over here we have the variational derivative dE d psi in the exponent. But the thing is, that's not actually the quantity that we had any information about in terms of inequalities. What we had information about was dE d psi minus the Lagrange multiplier L. Okay? That's the thing whose sign we know. So it would be great if we could get a minus or a plus n times L over here in this exponent without messing this stuff up. So that's easy to do. That's sort of the last little step here. So we'll define a new matrix, unknown matrix C in terms of B. That should be a capital N, I'm sorry, by this formula here. So we're just conjugating by e to the nl sigma 3 over 2, like that. And the effect of this in terms of the jump condition is exactly to add plus n times L in the off-diagonal entry. And that's it. So anyway, so this C is easily seen to solve this problem. Okay, oops. To solve this problem here. So C is an analytic function of Z, except on the real line. It takes continuous boundary values from the upper and lower half planes, and they are related by this formula that has this extra e to the nl there. And finally, C goes to the identity at infinity. That was not messed up by our conjugation. Okay, so yes?
Can you emphasize? Well, have you already explained the equilibrium measure is the best way to construct a G function?
I don't know the answer to that question, but it's a sufficient way to construct the G function. So in terms of asymptotic analysis, right? It doesn't actually matter what kind of we may disagree actually on our asymptotic expansions in terms of things like terms that are exponentially small beyond all orders, right? You and I may expand the same function and get two different series to expand the same function. We would both be substantially correct, but we may disagree in terms that are beyond all orders, right? And so, I want to say that there's no such thing as a unique asymptotic expansion for something, unless, of course, someone tells you what the functions are in your expansion whose coefficients you must find, right?
But you have found this as the way you are trying to construct A, B, C, D, E is trying to make the computation simpler.
Right.
So have you, at least up to now, have you...
Fair question. Let me say a couple things, okay? So in the problem of understanding orthogonal polynomials is a central problem in approximation theory. And people who work in approximation theory know about the equilibrium measure. They've known about the equilibrium measure since before the time of Sega, okay? So it's a very familiar concept for them. And one thing it's kind of, so they know how to use the equilibrium measure before Riemann-Hilbert problem kind of appeared on the scene, which was only around 1998 or so for this problem. Before that time, there was great understanding of equilibrium measures and how they could be used to study orthogonal polynomials. So it's a natural thing from that point of view to try to use the equilibrium measure that those people already understand to simply fix the Riemann-Hilbert problem and make it better. And that's a sort of point of view that I think is worth to emphasize. Okay. So we've arrived at this C. So these steps I've had up here the whole time. That A to B to C is sort of, I think of that as a stabilization step. So we're somehow trying to stabilize the Riemann-Hilbert problem, and the claim is that by putting in this equilibrium measure and then factoring off this L, so as it appears up here, that has had the effect of stabilizing our Riemann-Hilbert problem in the sense of controlling things as n goes to infinity. So what I want to say about it is if we think about those variational conditions, 10 and 11, which tell us alternately that in the support, this exponent here is equal to 0. And outside the support, this exponent here has a definite sign. Okay, the sign is negative. So that means that this off-diagonal element is either constant, or and 1 for that matter, or it's exponentially decaying to 0 if n is large. And that's the reason why this may be considered a stable problem. Also, here we just have some kind of oscillation. These are bounded because theta is real valued. Okay, so that's the idea. We've sort of stabilized Riemann-Hilbert problem 1, but now what we should think about is how can we take advantage of this kind of stability of the problem. So now we will sort of move on to the next step. So are there other questions about the stabilization step so far? All right. Okay, so the next step is the one that I mentioned, is the one that gives the method its name. It's the steepest descent step. So assuming that V is a convex analytic function, the support of psi is an interval alpha beta, and psi is analytic in this interval alpha beta in the interior. So then, using the fact that this psi, this theta, that's an antiderivative. It's an integral of psi, and this psi has mass 1. So that means that theta of x is exactly the constant 2 pi if x is less than alpha, and it's exactly 0 when x is greater than beta. Okay? So that means, yes? Sure.
So just now you show us one way you can just one. How about you have two holes?
Yeah. So you can also do this in the case of a non-convex V. You can have multiple intervals of support of your equilibrium measure. That does happen in some problems. So I'm just, for simplicity, I'm sticking with the case of one interval, but everything works in some. There's some equivalent way to do it for multiple intervals. It's a little bit harder to explain when I get toward the end. You'll see I can point out where it gets more difficult. Okay. All right. So anyway, so that means that if we're outside of the support, then these e to the I thetas are both equal to 1, and we have this thing. And that one is exponentially small because this L minus delta E is a negative quantity. So this is an exponentially small perturbation of the identity jump matrix, okay, as n goes to infinity, as long as x is fixed outside the support. All right, so now what about inside the support? So inside the support, that now I have this exponent is 0, so I have 1 here, and I have e to the plus or minus in theta on the diagonal, and because psi is positive in the support, this theta of x, it's a real analytic function, and it's strictly decreasing in this interval. So there's a monotonicity of that phase, okay? So we're going to think about how to use that. So this one already looks very good. This is like a small norm jump matrix somehow, identity plus very small, right? This one is not, because it has these oscillations here, and we have to figure out how to deal with that. But we see that this theta is a real and increasing, strictly increasing function on that interval. Okay, so that's the key. So this theta, it's an analytic function by our assumptions, so it solves the Cauchy-Riemann equations at every point of this interval alpha beta. So if x and y are the real and imaginary parts of z, then we have inequalities like this. So the partial derivative of imaginary theta with respect to y at some point on the axis is equal to the partial derivative of the real part with respect to x, right? That's the first Cauchy-Riemann equation. That holds for every x between alpha and beta. So since the real part of theta is equal to theta, and the imaginary part of theta is 0 on the axis, okay, that's because theta is a real analytic function there. And since this theta is strictly decreasing on alpha beta, then that means that this function, theta of z, is analytic function of x plus I, y. It has a negative imaginary part when y is small and positive, and it has a positive imaginary part when y is small and negative. Okay, so there's a sign to the imaginary part that comes from the monotonicity along the real axis of the real part. So this implies that this factor, e to the negative in theta, this is oscillatory when z is real, but it's exponentially small for large n when z is fixed in the upper half plane just above this alpha beta interval. And the other one is exponentially small when z is fixed in the lower half plane just below that interval. So the idea is that maybe we could take advantage of these facts if there were a way to somehow separate those two exponential factors so that one of them could be pushed into the upper half plane and the other one could be pushed into the lower half plane. That's sort of a neat idea. So that's where the steepest descent thing comes in. So here's this matrix. We can algebraically separate these factors by a factorization of this matrix that's pretty elementary, like this. This is like a lower triangular factor, a twist matrix, and another lower triangular factor here. So upper is lower, twist, lower. You can think of it like that. So now you see that the two different exponentials are algebraically separated on opposite sides of this constant off-diagonal matrix. So that suggests that we could now get these things into the half planes where they're exponentially decaying by just a substitution like this. So instead of the matrix C, we're going to define a new unknown matrix, dn of z, in this way. So outside of we call these contours a lens. It looks like a kind of contact lens or something like that. So outside of the lens, d is defined to be equal to c, okay? But inside of this upper lens here, we'll set dn equals cn times, well, what is this one? This is just the inverse of this factor over here, okay? And over in the lower half plane, in the lower half of the lens, dn is equal to c times this matrix. That is just this factor over here, okay? So these are both analytic functions by our assumptions on v and theta.
There's a negative sign.
This one has a negative sign. That's the inverse of this matrix here. Right? So what I'm doing, this is like remember we have C plus equals C minus times this. So I take this one, I put it on the other side of the equation as its inverse and combine it with the C plus. And that's what's over here. So C plus, it's like upstairs in the upper half plane. This is the inverse of that factor. So those go together. And down here, I have C minus times this one. Those are next to each other. So I will just combine them and call that D inside of the lens here. And then the jump for D that's left over, this part right over here, is just going to be that matrix. That's all. Okay? So the matrix Dn of Z, it satisfies its own Riemann-Hilbert problem, which we just did the calculation just now, relative to a more complicated contour, which consists of the real line together with this lens boundary and this lens boundary. So now our contour has gotten more complicated, but here's the Riemann-Hilbert problem for D. So we're looking for a 2x2 matrix Dn of Z. It should be analytic for Z in the complex plane. Take away the contour, the real line, and those two lens boundaries. Dn extends continuously to its jump contour from each component of the complement. It's taking boundary values D plus and D minus on the left and right sides. It's not just the real axis anymore, but we've oriented those two lens boundaries left to right, so they have a plus side and a minus side. So this is the formula for outside the support. It's exactly the same as before. This is, remember, exponentially small. This is the only thing that's left in the support interval for D. It's that central twist matrix, constant twist matrix factor. And then on the upper and lower lenses, we've got these factors here. And those things are now exponentially decaying to 0 for large N because Z is in the complex plane in the right spot. Finally, D is tending to the identity matrix as Z goes to infinity because we have not modified D outside of some compact lens. Outside of some compact lens. Okay. So that's the new problem. That's the steepest descent step. Okay. So this substitution has simply removed the outer factors in our three-factor factorization, placing them instead along curves in the complex plane where they're exponentially decaying to the identity matrix. And it's this step which is just some kind of a Riemann-Hilbert analog of what you do when you try to compute an integral and you have an analytic integrand. You try to move the contour of integration into the complex plane in such a way that something which is oscillating initially is turned into exponential decay. Okay, and then you can make an estimate of the integral. So it's this step that gives the name steepest descent method to the Dave-Joe technique. Okay. All right, so now this is the last bit, but we have almost an hour left, which is good because it takes a while to do this step. But still, it's quite interesting and useful to think about. And it's this step that will be different if we have multiple intervals, okay? So our strategy going forward is to observe that the conditions of Riemann-Hilbert problem 4 on this matrix D, they're simple enough that we might be able to build an explicit model function for Dn of Z. And such a model is called in this business, it's called a parametrics, okay? So the main idea is just to notice that the jump matrix for our D Riemann-Hilbert problem, it's converging pointwise on the contour sigma D to a limit matrix as n goes to infinity. There's actually a limit. So that it's not hard to find a matrix function that satisfies the limiting jump condition. And we will call that limiting matrix, solving the limiting jump condition, we'll call it an outer parametrics, okay? And the thing is that the convergence of the jump matrices to their limits, it's not uniform close to the endpoints alpha and beta. You know, we've used some inequalities that rely on x being away from these points alpha and beta. For instance, you know, the inequality for being outside the support of the equilibrium measure, that requires that we stand some distance from the support of the equilibrium measure in order to obtain the exponential decay of the off-diagonal jump matrix entry. And similarly, we did this Cauchy-Riemann argument to open up the lens, and well, we're saying that if you're in the complex plane, those exponentials are exponentially decaying, but those lenses have to come back to the real line. And that means that there are some z values close to alpha and beta where we are not getting the strongest exponential decay. So these approximations, this pointwise asymptotic of the jump matrix is not uniform near alpha or beta. And at the same time, as you'll see, the outer parametrics is going to have a singularity at alpha and at beta. So what we're going to need to do is to construct some different approximate solutions of the Riemann-Hilbert problem for D close to alpha and beta, and we'll call those inner parametrices. So we're using sort of the language of boundary layer theory here. We're thinking that there's an outer flow which is kind of away from all the sort of interesting stuff, and then there's some boundary layer things, which are like inner expansions close to these points, alpha and beta. Those are like the boundary layers, okay? And then, anyway, the outer and the inner parametrices, they can be combined into a piecewise formula that we call a global parametrics, and we believe that that global parametrics should be a uniformly accurate approximation of this dn of z. And then that's the thing that we will try to prove, and the way we do it is we'll compare dn of z with its parametrics. And the comparison will be a matrix called en of z, and we will check that that solves a small norm Riemann-Hilbert problem. That's the strategy. Okay. Okay. So, all right. So, as a consequence of our preparation, which means that we picked the g function the way we did, and we opened the lenses the way that we did, the jump matrix relating the boundary values of dn on the contour sigma d, it's got this pointwise limit as n goes to infinity. And in fact, the only part of the jump contour on which the limit is not the identity matrix, which means that there's no jump at all for d in the limit, the only part is the support interval alpha beta. And that looks simple enough that we could solve it explicitly. So let's try that. So we're going to look for a 2x2 matrix valued function. We'll call it d hat for parametrics and out for outer parametrics, d hat out of z. And that's supposed to be analytic for z in the complex plane, take away alpha beta. It should go to the identity just like d is supposed to as z goes to infinity. And it's going to solve exactly the jump condition that d solves on the interval alpha beta, which is this. This is the factor that was left in between the lenses, okay? Well, so how do we solve this? This is a constant matrix, okay? So we could diagonalize it. In fact, the eigenvalues of this matrix are just plus or minus I. And so here's a way to diagonalize the matrix using a unitary matrix U. This is its inverse or Hermitian conjugate, and this is the matrix U, okay? So we've diagonalized now this jump, so we could try to diagonalize this D out as well and solve some diagonal problems. So let's see how that works. So if we take the matrix F related to D hat out by a conjugation, by the same eigenvector matrix like that, well, if D hat out goes to the identity, then because this is a unitary matrix, so will F go to the identity, okay? The jump condition on alpha beta is simpler now because we've diagonalized the jump matrix. So F plus equals F minus times I sigma 3 is what this is, I 0, 0, negative I. Okay, so F has a diagonal limit at infinity, the identity. F solves the diagonal jump condition here. So we could try to look for F as a diagonal matrix, diagonal F1, F2. And Fj of z should be analytic in the complex plane, take away alpha beta. Fj should go to 1, as z goes to infinity. And then the jump conditions look like this. So F1 plus equals F1 minus times I, and I'm writing I in exponential form like this. And similarly with F2 and minus I written in exponential form like that. So this is a pair of scalar Riemann-Hilbert problems for Fj, and it's again similar to Riemann-Hilbert problem B that Riemann considered in his thesis. So we should take logs to try to solve the problem. So that's what we're going to do. So we'll write Fj of z in the form of e to the Lj. L is some kind of logarithm, right? And these, we're going to suppose that the Lj's are analytic functions for z in the complex plane, take away alpha beta, but since the f's should go to 1, I want the L's to go to 0 as z goes to infinity. And so then the jump conditions for Fj have been converted into an additive form like this, using the properties of the exponential to take quotients, right? So L1 plus minus L1 minus is I pi over 2, and similarly for L2. So now you could use the Plumel formula to write some formula down for these L's. So L1 and L2 turn out to be opposites, and we'll take the Cauchy integral of just I pi, constant I pi over 2 over the interval alpha beta. So that's this integral here, and when we compute this, we should just evaluate the logarithms like this and take principal branches, and then we have a formula for L1 and L2 in terms of principal branch logarithms, and there's this 1/4 here. So that means that when I exponentiate to get back Fj, f1 is the reciprocal of f2, we'll call that common function gamma of z. It's some kind of 1/4 power of this fraction, z minus beta over z minus alpha. And we're going to choose this thing in such a way that its branch cut is exactly between beta and alpha, and gamma goes to 1 at infinity. Actually, if you put such a formula into Mathematica, and which knows about principal branches, this formula will produce exactly the right thing, okay? Makes a straight line branch cut between those 2 points. Okay, so that's our gamma. So consequently, this matrix, so now we have to undo it, so we reconjugate like this. We take gamma to the sigma 3, conjugate by u, that's called d hat out, okay? So that thing is a solution of the pointwise asymptotic of Riemann-Hilbert problem 4, and this function d hat out, it defines our outer parametrics for dn. So I would like to observe that even in the symbols, there's an n, which is our matrix size parameter in random matrix theory over here, and there is no symbol like that over here, and that's because this quantity does not depend on n at all. It's completely independent of n, and somehow that means that the n dependence in what we need at the end for our polynomials, it's all hiding in those transformations that we've already made. It's really interesting. Anyway, so that's the outer parametrics. It doesn't depend on n. Its determinant is exactly equal to 1. So by the way, this is the place where if we had multiple intervals of support for our equilibrium measure, we would have to work a lot harder here. And the reason is because if you take the complex plane and we put in a branch cut between alpha and beta, a single interval, well, with a square root, there's really 2 copies of the complex plane, and they are glued together across this branch cut. But that means we have a hyperelliptic surface, and the genus of that surface is 0. So all of our function theory on that surface is elementary. Okay, we can map it to the Riemann sphere, and that's why we can solve this problem in such a simple way. But if we had multiple cuts in our problem, then we would have a higher genus Riemann surface, and we would have to use the function theory for such a higher genus Riemann surface, which is elliptic function theory in the case of 2 cuts, and hyperelliptic function theory, theta functions, and so on for more cuts. So that's the reason why I'm not doing it in the lecture, but it's all doable, it's just more complicated, okay? Anyway, so the elements of this outer parametrics, you could see from here, remembering that this gamma has got the 1/4 root on it, right? That means that the elements of this matrix are going to blow up like 1/4 powers. This should say z naught is alpha beta. So they blow up like -1/4 powers. All the elements of this matrix do. So the singularities that are showing up, you might think you could get rid of them by choosing different solutions in the limiting jump conditions, which differ by some rational functions with poles and zeros at alpha beta. In other words, taking the logs differently when we use this technique to solve the problem. But in fact, the solution that we've already written down here is the one with the mildest singularities that are possible. And anyway, the blow up is a problem also because the Riemann-Hilbert problem insists that dn should take continuous boundary values on our jump contour. So that's a problem. So we have to repair that, but we also remember that that our limit n to infinity of the jump matrix was not uniform close to alpha or beta. So we have to do something else near alpha and beta anyway. That's exactly where this matrix blows up. Okay, so that's what this says. It's also true that the pointwise convergence of the jump matrix that we use to motivate the outer parametrics is failing near the endpoint. So we're going to have to make a better local model for dn near alpha and beta that's going to more accurately capture the true jump conditions. And in fact, what we're going to do is solve the jump conditions for the dn problem exactly near these 2 points. So going forward, what I'm going to do is I'm going to make a generic assumption. I'm going to assume that the density psi of the equilibrium measure vanishes exactly like a square root and not like some higher power like 3/2 or 5/2 power near alpha and beta. So in the 2 cases that we wrote down by examples, you can just see that that's true. And I'm just telling you that it's a generic condition. So you can make up examples, specialized examples where it fails, but in general it's true, and it's certainly true in these 2 examples. So let's assume that we have square root vanishing of psi near alpha and beta. And so now we're going to give all the details of how to do the construction near beta, and then you'll see that it's all very similar for z near alpha. Okay, so the main idea is to look very carefully at the jump matrix for dn near beta. So the function theta of z is positive, and it's decreasing to 0 for real z less than beta. And it vanishes like a multiple of beta minus z to the 3/2 power, according to our working assumption that this psi is vanishing like a square root because theta is an integral of psi. So it's like a 3/2 power. So in fact, you can show that this function here, w of z, is just minus theta of z to the 2/3 power. That may be regarded as an analytic function of z in a full complex neighborhood of z equals beta. You can also check that if you plug in beta into here, you're going to get w equals 0. And if you differentiate this function, it's got a positive derivative at beta. And what that means is that this formula here, w equals w of z, given by that quantity, is a local conformal mapping between a neighborhood of z equals beta in the z plane and a neighborhood of w equals 0 in the w plane. So you can just transport things back and forth all you like. So obviously that's going to have a nice effect on the jump conditions that involve the function theta, because they can be written in terms of w. But what I want to really show you is that if we consider this thing, which is in the off-diagonal elements of our jump matrix, so right, f of z is L minus the potential v of z plus 2g. Let's consider that in the upper half plane, okay, for z. So if we take a boundary value on the real line to the right of beta, then we have f plus is L minus v plus 2g plus, but g plus to the right is related to g minus by g plus equals g minus. That's right. So that means that we can replace 2g plus with g plus g minus. Okay? And then this expression here is just the quantity that we have some control over for x greater than beta. This is L minus the variational derivative of the energy evaluated at x. That's the thing that's showing up in our exponent, by the way, when x is greater than beta. This quantity is really just the plus boundary value of this function f. But on the other hand, if you take a boundary value of the same analytic function, now for x less than beta, f plus of x is this same expression here, but now g plus and g minus are related in a different way, because this identity holds true in the support. So this expression is nothing but g plus minus g minus, which is I times theta of x in the support interval. So we can then write that in this way. It's I times the 3/2 power of minus w, when w is a negative quantity. So what we're saying is, by analytic continuation through the upper half plane for w, we can express this quantity here, which is showing up in our exponent, as just minus w to the 3/2 for w positive. Okay? So what I'm saying is all of the jump conditions have been written in terms of this conformal map w. All the jump matrices for d in a neighborhood of z equals beta have been written in terms of this variable w. And there's also an n floating around, but if you don't want to look at n, you can scale it out by setting zeta equals n to the 2/3 times w. And then the jump conditions for dn of zeta near z equals beta can be written in the zeta plane in this way. So the jumps are now happening when zeta is positive, when zeta is negative, and when zeta is in, n to the 2/3 times the image under w of these lens boundaries, L plus minus. But look, all it is just e to the minus zeta to the 3/2, e to the zeta to the 3/2, and this twist. That's it. So everything is just involving zeta only. Very nice. And the same powers, in fact. So now, as these contours L plus minus, these lens boundaries, are sort of arbitrary to some degree, we're going to pick them so that in some fixed neighborhood of z equals beta, the images of those lenses under the conformal map are just straight line segments that meet w equals 0 at these two angles, plus or minus 2 pi over 3. So here's a picture. So this is the z plane, okay? We have these lens boundaries coming in. There's the point beta, like this. And when we map this to the w plane, we're going to assume that the image of this curve is this straight line here. And the image of this curve is this straight line here, okay? So that's the w plane. And now in the w plane, we have these very nice jump conditions that are written in a simple way in terms of W or the scaled version of it, which is zeta. Okay. So now we're going to find an exact solution of these jump conditions to use as an inner parametrics for this dn of z in some fixed z neighborhood of z equals beta. So the question, we know the jump conditions that it should satisfy nearby. We just wrote those down. But the question that we have to answer is what should happen when zeta starts to become large? Zeta being large is the same thing as saying that W is just kind of on the boundary of this disk at some fixed distance away from W equals 0 because n is large, okay? When we think of n being large, that's going to expand in the zeta plane, that boundary out toward infinity. So we need to figure out how should the solution of our jump conditions behave as zeta goes to infinity. So what we're going to do to sort of motivate our assumption on this end is we're going to consider that the inner parametrics that we're going to try to build, it should somehow, not fight too much with the outer parametrics that we already constructed. So we constructed this function which should be a good approximation of D everywhere in the complex plane except in two disks. And now I want to put something in those disks that should not be too different from what that function is, at least on the disk boundary. I don't want to cause too much trouble, so I'm trying to make a good match on the disk boundary. So that's what this says. I want to match the outer parametrics. So let's write the outer parametrics in terms of this zeta as well. So here's gamma of z. That's the thing that's in the middle of the definition of the outer parametrics. So z minus beta over z minus alpha to the 1/4. So you can write that as like gamma tilde of z times w to the 1/4, where gamma tilde, that's a function analytic and non-vanishing in some fixed neighborhood of z equals beta. So basically I'm factoring out this part, and I'm saying, well, that's harmless. That's like a non-zero analytic function close to beta. And what's left over, I could write it in terms of this conformal mapping. It's something that's got to vanish in the conformal variable like a 1/4 power, because I have z minus beta to the quarter, so it ought to be a w to the 1/4. Everything else I will just call gamma tilde of z. Okay, so then what is this? Well, if we write w to the 1/4 in terms of zeta, I'm going to pull out an n to the negative 1/6, that's all, and then I have a zeta to the 1/4. All right, so that means that I could write this outer parametrics in a neighborhood of z equals beta. I could write it in this form. So it's some holomorphic prefactor in the front times zeta to the sigma 3/4. That's directly coming from this part right here, times u dagger, and u is our eigenvector matrix that we had before. This hn of z is everything else in our formula that we pull out to the left of this factor. So there's no zeta over here. This is this non-vanishing analytic function. There's some factor that depends on n, and there's our constant eigenvector matrix. But this is analytic in our disk, and the only thing that's going to come in from our jump conditions is this thing right here. That's the only part that's contributing to the jump. Okay. So let's temporarily ignore that analytic prefactor, the hn of z, because we're going to put it back in later. And what we're going to do is look for a matrix-valued function of zeta that satisfies the exact jump conditions for dn, written in terms of zeta, but also it should match well onto the remaining two factors, these guys here, of our formula for the outer parametrics as zeta goes to infinity. So that means we're going to look for a matrix, we'll call it z of zeta, that satisfies a Riemann-Hilbert problem relative to an unbounded contour that is this one now in the zeta plane. So we have the real line, we have these two lines which have an angle of 2 pi over 3 from the positive real axis, both incoming. So sectors 1, 2, 3, and 4 of the complement, okay? So let me write down that Riemann-Hilbert problem. It's this one. So let's try to find a 2 by 2 matrix-valued function, z of zeta, that's analytic in the complex plane, take away this crazy contour. It extends continuously to the contour from each of the 4 sectors, and it takes boundary values that are on those sectors related by these jump conditions. So for the positive real line, we have the jump condition written in terms of the zeta variable for z bigger than beta. That's what that is. And then here's our twist matrix for zeta less than 0, which is the image of the interval alpha beta in our problem. And then here's the two lens boundary jump conditions on those two straight lines. Arg zeta is plus or minus 2 pi over 3. And then the normalization is that this z should be matched to these terms, because those, the inverse of this, that was the right-hand factors in our outer parametrics once we wrote it in terms of the zeta variable. So I want this to tend to the identity matrix, because then I will have something for large zeta, which is the same thing as w being sort of fixed distance away from 0, but n being large, and that will be almost the identity. So that's a very good match. Okay, anyway, so one might wonder, I just made this problem up. It sort of came from thinking about, matching things onto other things, and it certainly is not equivalent in any way to what we started with. Unlike the other sequential Riemann-Hilbert problems that we've been writing down, this is sort of a dream to write this. But what I want to show you is that this problem, we can solve this explicitly with the help of some special functions. It's a very special Riemann-Hilbert problem that's on this slide, and it can be solved in terms of the Airy function, as we will see. So it turns out that this problem has a unique solution whose determinant is exactly I, which, by the way, that's just the determinant of our matrix U that showed up in our eigenvector computation, being minus I, I'm sorry. And moreover, we're going to build this matrix Z explicitly. So the first step is to notice that if we take the Z matrix and multiply on the right by this factor, e to the minus zeta to the 3/2 sigma 3 over 2, just like that, then it turns out that in terms of this W, the jump conditions for the problem become a lot simpler. They're piecewise constant. So that exponential has been peeled off completely by this transformation. So now on the positive real line, I have this jump matrix, 1, 1, 0, 1. The negative real line is unaffected, and the reason for that is that the branch cut for these fractional powers is exactly the negative real axis. So those don't have any effect. I mean, this matrix has no effect on the negative real line, and we have the same jump condition as before. And then on those two lens boundary straight line contours with arg zeta plus or minus 2 pi over 3, we have 1, 0, 1, 1. So the jump matrices are just constants now, okay? But we pay a price for that. The simplification leads to a price, because now that same exponential factor has to show up in the jump condition. So this quantity that I'm circling, that's our original matrix Z of zeta now. So it's got now for W, there's an exponential that's appearing there. Okay, but now we make an observation. So since the jump matrices for W, they're all constant on each arc, on each of those rays, it's a constant matrix. That means that the matrix dW d zeta, it satisfies exactly the same jump conditions that W did. So that means that you could apply this Morera or generalized Cauchy argument to look at this thing. So dW d zeta times W inverse. Look at that. And let's call that Y of zeta. Well, that should be an entire function of zeta. Okay? Well, how do we figure out what an entire function is? The only thing we could possibly do is ask how it behaves when zeta is large. So if we interpret this expression as saying that that this quantity here has got a Laurent expansion, asymptotic Laurent expansion for large zeta, identity plus zeta inverse times some constant matrix B plus smaller, and also that the derivative of this quantity can be expanded as the derivative of this series. So that's a kind of a hypothesis, but it's the reasonable thing to assume, I think. Okay, so this would be the derivative of that. So if that's true, if these things are true for some constant matrix B, then it's very easy to work out from these formulas here what the asymptotic behavior of this quantity Y of zeta should be. And the answer is this. So Y of zeta should be 3i over 4 times this linear in zeta matrix plus something that goes to 0 as zeta goes to infinity. So since Y of zeta is an entire function, and this is its large zeta asymptotic behavior, little o of 1 must be 0. That's Liouville's theorem. So this Y of zeta is a linear function. That's what it is. It's a linear function of zeta. And if we remember that Y is dW d zeta times W inverse, that means that W solves this matrix differential equation in which there's a coefficient matrix that has some constants that I don't know in it, and then there's zeta, which is just a linear function of zeta. So if we massage this a little bit, so let's set C to be 3/4 to the 2/3 times zeta minus this number, okay? Then it follows from elimination that every element of the second row of this matrix W solves this equation, and this, of course, is just Airy's differential equation, okay? So I'm just saying that in order for this Riemann-Hilbert problem to have a solution in any reasonable sense, the solutions have to be built out of Airy functions, okay? That's what I'm saying. All right, so just a review about it in case you're unfamiliar. So the differential equation is the Airy equation, and its solutions are nice, handy special functions. So one particular solution of it is given by this contour integral. It's called the AI of zeta function, or the Airy function, AI of xi, I'm sorry. So it's this, so 1/2 pi I times the contour integral of this simple exponential here, dz, and so the xi, that's the independent variable, is just showing up like that. It's like a Laplace transform, inverse Laplace transform integral. And the C contour is any contour in the complex plane that starts at infinity with arg z is minus 2 pi over 3, and it ends at infinity with arg z is 2 pi over 3. So something like this. Okay. So anyway, it's a real value. This is a real valued function here. This is a real valued function of real xi. And here's the red curve is its graph, and the blue one is its derivative. Okay, so that's what the Airy function looks like. All right, so given that AI of xi is a solution, it's easy to check, and we already used this fact in the first lecture, that AI of xi e to the plus or minus 2 pi I over 3, these are also solutions of the same differential equation, but it's a second order equation. It only has two independent solutions, so there's got to be a relation, and using the Cauchy theorem you can check, and this contour integration you can check that this connection formula holds true. So these three solutions are not independent, they're related by this identity here, and that's the only independent linear relation among the three solutions. And we also used these formulas before, so because you could write the AI function as a contour integral, you can use these classical steepest descent method to write down asymptotic expansions, or if you like, you can look them up on the digital library of mathematical functions, and these are the large xi expansions, which are true as xi goes to infinity in any direction of the complex plane except the negative real axis. And so, in other words, the Airy equation demonstrates a Stokes phenomenon, just like the Painlevé direct problem does. And so, in this case, it's the negative real line that's the Stokes line for the problem. Okay.
So in this context, the saddle point really means zeta at infinity.
Sorry, which the saddle point?
Saddle point.
Well, I mean, for these to calculate these formulas here, the saddle point is so you take the derivative with respect to z of this, and it's a quadratic, right? Which depends on xi. There are two of them, and they move around in the complex plane depending on the complex value of xi. And then you have to, as you say, you have to move the contour to pass the saddle point, and that's where these formulas come from. Okay. All right, so we know a lot about this, so this second row anyway. So we first construct the matrix W in sector 1, which is the one where arg zeta is between 0 and 2 pi over 3, okay? So here, as a basis of solutions of Airy's equation, we're going to choose the AI function and this particular rotated version of it. So if you go and look on the digital library of mathematical functions, they will tell you that when zeta is in this range, when zeta is in this range, which also, by the way, means xi is in that range because they are related, right? What's the relation? I forgot. It's this, right? So it's just a shift and a positive multiple. So the directions are the same. Okay. So if you look on the digital library, they will say that if you're interested in this region here, you should choose what they call a numerically satisfactory fundamental pair for the equation, and they will tell you that these two functions form a numerically satisfactory fundamental pair. So that's how you work it out, actually, is you look at the digital library to figure out which basis you should pick for each sector. So for this one, I will choose these two, okay? And then since our asymptotic formula hold in every case as c goes to infinity in the sector, so now, okay, so that's what I'm saying. So the formula that we just wrote down, those two asymptotic formulas for AI and AI prime, they are both valid using these two functions in this domain. That's another way to think about numerically satisfactory fundamental pairs. Okay, anyway, so we're going to take a general linear combination, A1, B1, and A2, B2, like that. And so the second row elements of our matrix in this sector, we could write them as these functions for some constants that we have to pick. So what do we have to do? We should try to make this formula solve the normalization condition. So we calculate row 2 of the normalization condition, and we get that these two functions multiplied on the right by this exponential, our eigenvector matrix, and this power function, it should behave like this. And these e's have the following asymptotic expansions coming from what we just wrote, and the Airy function expansion. So E1 is this crazy thing. But anyway, exponentials are showing up, powers, and the constants. This is important. The constants that we have to determine are showing up here. And this is E2. So what our normalization condition requires is that in the same limit, this expression should be 0, 1 plus this quantity times 1 over zeta. These are two constants that I don't yet know, plus smaller. So I have to kill a lot of terms here, is the point. So the first thing is to notice that the asymptotic formulas that we wrote down, they contain exponential terms like this, unless B1 and A2 are both 0. And these factors here, they grow exponentially in different halves of sector 1, and that means that they're inconsistent with the asymptotics that we're trying to enforce. So that means we must choose these two things to vanish. So B1 is 0, A2 is 0, and now we have simpler things to stare at here with just fewer constants, okay? So we have to still compare with this expression. And now that we see that there's still something offending us here, there's still something exponential, but it's just a zeta to the half in the exponent, but there's something exponential there. Okay, so we should get rid of that by choosing the c to be 0, and that's actually the only reasonable way to do it. Otherwise, you're forced to take all these constants to 0, and that again would be inconsistent. So we really are forced to choose that c to be 0, which means that we have this relation on those unknown constants b11, b22, and b21 squared. Okay, that's got to be 0. And so now we again write this out. Zeta goes to infinity in our sector. Now E1, E2 look like this. So again, we have to compare with the same expansion down here. And we see now that this thing is somehow a problem. It's still decaying quite slowly compared to anything that's standing over here. Okay. Great. Okay, so the final problematic term is the part of E1 that's decaying like a square root. And that's too big because we need this decay to be like 1 over zeta. So that its coefficient should be 0, and that's this identity right here. And so then to get the normalization correct for the second one, that's where we pick the constant term, and we pick this is equal to the constant term. Okay, so now the expansions have reduced to this form, like that. And again, we compare for one last time with this formula down here. And now we see that B21 and B22 are both equal to 0. So now we remember that C is 0, and that means B11 is also 0. So all these things turned out to be 0, and we've picked the constants in a unique way in this sector. So taken together, these equations 34 and 35 tell us what A1 and B2 have to be. So we've determined the second row of W of zeta as a certain linear combination of Airy functions in sector 1. It has to be this. And we also learned, because we figured out something about those constants B, that the differential equation for W of zeta actually has a simpler form. It's really just this thing, which is much more easy to see that it's related to the Airy equation. Okay. So, all right, well now that's the second row, but the second equation of the system tells us how to get the first row from the second. All we have to do is take some derivatives and multiply by some appropriate constants. And so now that means that W11 is something involving AI prime. W12 is also involving AI prime at the rotated argument, okay? So now we apply the asymptotic formula for derivatives of area functions, and you see that as zeta goes to infinity in sector 1, this quantity here is 1 plus small and small. So that's exactly what we needed to happen. So there's no further conditions that we have to impose, and there was also nothing that we had available to satisfy the conditions. It just worked out. So to conclude, for arg zeta between 0 and 2 pi over 3, W, this is sector 1, W is the sector 1 formula of W of zeta, and it's necessarily given by this rather complicated looking expression, but it's really just systematically obtained, I have to say. You just write the general solution of Airy's equation and expand it for large zeta and match it onto the asymptotics. So this completes the construction of W of zeta in sector 1.
This is sector 1.
Sector 1 is, yes, sector 1 is here. Yeah. All right, so we've just finished it in sector 1. Now, you might think we have to do this now for sectors 2, 3, and 4, and you can, but we could also take advantage of something else. So it's easiest, I think, just to take advantage of the constant jump conditions that the matrix W is supposed to satisfy across each of these jump contours. So for instance, if we want to get into sector 2, okay, in this diagram, then we should relate W2 to W1 using the jump across this segment here, and that's just this constant matrix here. All right, so we just take the W1, we do the multiplication, and we get something involving combinations of Airy functions. And it's handy to then use that. This is the identity involving the 3 different rotations of the Airy function adding up to 0. It's useful to use that identity to write the result for sector 2 in terms of these 2 guys, because those form, according to the digital library of mathematical functions, a numerically satisfactory fundamental pair in that sector of the complex plane. Okay, so that basis of solutions, what they really mean is it has no Stokes phenomenon in the sector of interest. Okay, so the result is that in this domain, the formula for W is given by this combination of AI and AI primes for these rotated arguments. Okay? So you just move in this way from sector to sector. So this is the formula in sector 4, it looks like this. And in sector 3, it's this formula over here. And then you just check that in every single direction of the complex plane, no matter which of these formulas I pick, if I multiply by this factor and I use the asymptotic formula for the Airy function to take the limit, I'm going to get identity plus small, and this is how small, okay, as zeta goes to infinity. Then you can also check, you have formulas here, so you can calculate the determinants of these matrices, and that means you're going to be computing some Wronskians, as you can see, of Airy functions. But those are also tabulated, and if you look them up on the digital library, you can find the Wronskians of any 2 of these things, and that shows you by direct calculation that the determinant of this matrix W of zeta is exactly I, no matter which of the 4 quadrants you work in. Okay? All right. All right, so now we're almost done with building this inner parametrics. Let's recall the holomorphic prefactor Hn of Z. So remember, we took the outer parametrics and we resolved it into a holomorphic prefactor close to beta. And then there was some other terms that we could write in a convenient way in the variable zeta. And that's the part that we use to normalize this Riemann-Hilbert problem. But then we have to put back this holomorphic prefactor. So the thing about prefactors, that means multiplication on the left, is that they don't change any jump conditions. So we may just put it back in. And so as our model for dn near z equals beta, we're going to call this d hat n, because n does show up in this formula, sub beta of z. By definition, that's the holomorphic prefactor Hn of z times the solution of the problem that we just built. Actually, we just built w, but then you put back the exponential to get z. And we evaluate that at zeta equals n to the 2/3 times w of z. W of z was our conformal mapping. Okay, so here's the whole thing written out in terms of the matrix W that we just wrote on these last couple slides. So, as we mentioned, and we used already in lecture 1, multiplication on the left by a holomorphic matrix factor, like this Hn of z, it has no effect on jump conditions. And so that means that, because the jump matrix for Z, it was just a re-expression in terms of the conformal coordinate of the one for dn of Z. This quantity here is an exact local solution of the jump conditions for dn, okay? It solves everything exactly nearby. And a similar procedure carried out near Z equals alpha, which we're not giving the details of here, results in a second inner parametrics that we'll call d hat n sub alpha of Z, and it's got completely analogous properties. It's an exact local solution of the jumps near Z equals alpha, and it's going to match in a nice way onto the outer parametrics. Okay. All right, so now suppose U alpha and U beta are two small disks of some radius that's independent of n, and they're centered at Z equals alpha and Z equals beta respectively. So then we're going to define our global parametrics in a piecewise formula like this. So d hat n of Z is going to be the outer parametrics, d hat out of Z, no dependence on n. That's as long as we're in the complex plane, but not in these two disks, either of these two disks. If we're in disk alpha, U alpha, we use the inner parametrics that is corresponding to local solution of the jumps for D near alpha, and in the disk U beta, we use the one that we just built that solves the jump conditions exactly for D in the disk U beta. So this matrix here satisfies determinant of d hat n is exactly equal to 1 at every point of its definition in the complex plane. So that was something we checked directly for this one. And for these, well, there was a W matrix whose determinant was constant. It was I. But actually, there's also this holomorphic prefactor, which has a determinant that's minus I. So the product makes it come out just right. Okay. Well, so now we're getting close. Now we want to get to this matrix E. So we want to compare our parametrics with the actual matrix D to arrive at a small norm problem. So the global parametrics that we just defined this piecewise formula for, it's now been explicitly constructed. And we can compare it with the unknown solution, dn of Z, of Riemann-Hilbert problem 4. And the way we're going to do that is just to define a new unknown matrix. We'll call it En for error. En of Z is by definition dn of Z. That's the solution of Riemann-Hilbert problem 4, whose conditions I understand, but the solution of which I don't know. And then multiplied on the right by d hat n of Z inverse, and the hat means parametrics. This thing I know explicitly. We just built it, okay? So from that, you can check that the matrix En of Z, it satisfies a Riemann-Hilbert problem because dn of Z does, and the global parametrics d hat n of Z is something we know. So here is the oriented jump contour on which, we'll call it sigma E, on which E sub n has jump discontinuities in the complex plane. So that jump contour does not depend in any way on n, and it consists of two circles with clockwise orientation, the real line outside of alpha beta, and also outside of these two circles with left-right orientation, these two lens boundaries outside of the circles, L plus and L minus. But the things that are missing are all of these arcs, 1, 2, 3, 4 arcs on the inside of the circles. That's because we solved the problem exactly there. And also the jump is missing on the interval alpha beta in between these two lenses, and that's because the outer parametrics has completely solved that jump condition exactly. So everywhere that d hat n has exactly the same jump conditions that dn solves, there's no arcs in the picture. Okay? So this is the jump contour for En of Z now. So the fact, as I said, that all the contours within the disks U alpha and beta, as well as the rest of the support interval, have disappeared is just because the outer parametrics and the inner parametrics, they're solving exactly those jump conditions. So now we might observe that this sigma E is an admissible contour with self-intersection points, and that motivates the need for this kind of general theory that we covered. So we started out with a problem with no self-intersection points. It was just a real line. But we had to make some substitutions along the way to try to get toward a small norm problem, And now we see that we have a complicated contour with self-intersection points. So it turns out it's not a complete contour. Maybe we look at it again. It's not complete. For instance, every complete contour should have 4 arcs, or an even number of arcs at each self-intersection point. And there's only 3 of them here. But as you know, we may simply modify this by adding some extra arcs and then changing the orientation on some as necessary, and then we'll have a complete contour. So that's not a problem. Okay. Right. So, so it's not a complete contour, but we can complete it. And furthermore, it's a consequence of our definition of the global parametrics that the Riemann-Hilbert problem satisfied by this En is a small norm problem when n is large. So let's write down what the En problem is. So En is a 2 by 2 matrix, analytic for Z in the complex plane. Take away the contour we just showed. It extends continuously from, this should be the complement, the complex plane take away sigma E. It extends continuously to the jump contour from each component of the complement, okay? And it takes continuous boundary values En plus minus of Z from each side of sigma E, and they're related as follows. So at each point of the jump contour, take away the 2 disk boundaries. En plus is En minus times identity plus something that decays exponentially to 0, uniformly on the jump contour as n goes to infinity. And at every point of the boundary of these 2 disks, delta partial u alpha partial u beta, En plus is En minus times identity plus order 1 over n, something that's uniformly of size 1 over n on those circles as n goes to infinity. And finally, E is normalized to the identity matrix as Z tends to infinity, because that was true of both of the factors that made up the formula for E. So let's see why the jump matrix is a small perturbation of the identity. So to prove the first result, which is the one of exponential decay away from the boundaries of the disks, you just have to observe that it already holds by the steepest descent that the function D, the jump for the matrix D, is already an exponentially small perturbation of the identity. And so the thing is, that was something that was true except close to alpha beta, but alpha and beta have now been cut out of this whole picture. And we're just talking about the part of the jump contour bounded away from those points, and there we have uniform decay of the jump matrix for D to the identity, exponential rate. So that's true, and so to compute the jump matrix for E on that part of the jump contour, well, we use the fact that D hat n is the same thing that the parametrics, which is the outer parametrics, because we're outside of the disks, it has no jump on those arcs. So that means that En minus inverse E plus minus identity can be written like this. So here's Dn minus D hat out inverse without a plus or minus, because they are the same. That thing inverse times a similar quantity for the plus side minus identity, and then you rearrange and you see that you're conjugating by this D hat out something in here which we just said is exponentially small, okay? And then you remember that because we are bounded away from those 2 points where those are the only places alpha and beta where D hat out blows up, this is a very good conjugation, and it preserves the asymptotic smallness of this quantity here. So D hat out and its inverse, they are bounded on this part of the contour, and so that guarantees that the corresponding difference here is exponentially small uniformly on the jump contour. Okay, so now the last one is to look at the disk boundaries. So for those, we notice that there's no discontinuity of D on the 2 circles. I mean, that's artificial, right? The jump matrix for D had the 2 lenses and had the real line, but it did not have these circles. That was a consequence of putting a parametrics in that was built from a piecewise formula. So there's no discontinuity of D on the 2 circles, but the mismatch is coming from the discontinuity of the parametrics. And that's the place where we tried hard to make the inner and the outer parametrices match onto each other. Okay, so E plus of Z on the circle, plus is on the outside because they're clockwise oriented. E plus of Z is Dn without a plus or minus times D hat out inverse, because out is on the outside. That's the outer parametrics. and then that's equal to dn times d inner parametrics at beta inverse times d inner parametrics at beta times d out inverse, just like that. This is the identity, okay? But now this one here is E minus, and this one over here, that's something that we have control over because we picked that normalization just right in Riemann-Hilbert problem 5. So the jump matrix here is this quantity. It's just the ratio of the outer and inner parametrices. So we write them out. So here is the inner parametrics formula written out, and here is the outer parametrics formula written out. And so that's just the conjugation by this Hn of Z, this matrix holomorphic in the disk centered at beta, times the asymptotic for the W matrix. So identity plus this small thing. Okay? That's because the boundary of this disk is at a distance n to the 2/3 away in the zeta plane. That's the reason why these factors are appearing exactly in the way that they are here. Okay, so then we calculate what this Hn is, we put that back in, and so that changes. The Hn has some n dependence that comes in and conjugates this matrix so that what appears at the end is just identity plus order 1 over n. So this n to the minus 2/3 is changed into a 1 over n. This n to the minus 4/3 is made slightly worse, order 1 over n as well. That's the conjugation by the Hn that does that. And what's left over here is bounded on the disk boundary, so identity plus order 1 over n as n goes to infinity, uniformly on that circle. Okay, so it's not much harder to show that the derivatives of the jump matrix for En along the different arcs also decay uniformly as n goes to infinity. And you can also check that the necessary consistency condition is satisfied by the jump matrices at the self-intersection points. And that's coming from something we mentioned earlier. If you start with a problem that's consistent and you make piecewise substitutions in the complex plane, you will preserve that consistency. Okay. So by completing the contour sigma E with suitable additional arcs that carry identity jump matrices, and by using the fractional linear mapping to compactify the jump contour, we conclude that this En of Z satisfies the conditions of a small norm Riemann-Hilbert problem, and that's something that we can then solve with the Neumann series. So if n is big enough, we can invert the operator with the Neumann series, and one of the things that comes out of that is just this very simple estimate that holds uniformly on the whole complex plane. So En of Z is identity matrix plus a uniform O1 over n as n goes to infinity on the whole complex plane. All right, so that's enough to tell us what we want to know. Since the unknown dn is uniformly close to its parametrics, so that's because we can just write this formula. dn is E times dn hat. This is something we know, that's the parametrics. This thing is uniformly close to the identity in the complex plane. We have this formula. And then we remember that dn is related to the original unknown an by a sequence of very explicit steps. So we just invert those steps. Okay? And at last we get asymptotically accurate formula uniformly in the complex plane for all of the matrix elements of this an of Z. So for instance, if we take Z to live in the upper half plane just above a point in the interval alpha beta, so then you can unravel the explicit relations between an and dn, and in this region, this is the formula for the matrix here. Okay? This is the asymptotic formula, and the only thing that's not exact here is En, and En is just identity plus order 1 over n, uniform. Okay? So the d out is an explicit thing, doesn't depend on n. This is the only place where n is showing up, here, here, and here. That's it. So we may recall that this G, L, and theta, they're obtained from the equilibrium measure. The d hat outer parametrics is this gadget, where gamma is this 1/4 power. And that means, I guess, that you can, for instance, come down from this upper half plane a little bit to the real line. You let epsilon go to 0, and you're going to get something that's a formula for the monic orthogonal polynomial in the interval alpha beta. So here's the formula that comes out. So you'll see that what this says, there's some exponential factor, okay, that depends on the potential, and this Lagrange multiplier is showing up as well. This is exponential. there's some sort of a power law here in terms of x minus beta and x minus alpha, and then there's a cosine. So the zeros of this polynomial are, roughly speaking, given by the zeros of this expression that involves an angle n times theta of x, okay? So this is a very rapidly oscillating function, and the density of zeros is roughly given by this derivative theta prime, okay? So this quantity v minus L is real valued, so there's exponential growth, but there's the fast phase, which is given by the equilibrium measure psi of y by this formula here. So the density of zeros is proportional to psi. That's what we're saying. Anyway, lots of information there. And then just a last comment, you can also get information about the derivatives of this an, because if you have a positively oriented circle of radius r that's centered at some point in the complex plane, it doesn't intersect your jump contour, then you can use the Cauchy integral formula to calculate the derivatives like this. And because you're always getting this en here in the integrand, it's always going to be 1 over n for all these derivatives. So the constant in this big O will depend on k, the number of derivatives, and r, which is this little circle that you're taking, or the radius of the circle that you're taking, but still you get this control on the error term. Okay. So here's the Fokas-Itzkatayev paper, and this is a great book with lots of information about logarithmic potential theory that's relevant to the computation of this g function and the equilibrium measure. So.
We just have the information of the orthogonal polynomial on the support of the equilibrium.
No, I wrote a formula for that, but you can write. Look, I mean so this formula here, actually, yeah, okay, that's fine. So this formula here holds true anywhere sort of above the support interval, but there's other formulas you can write that have some slight differences in them. Like, for instance, if I'm outside of the lens, then I would not put this factor in, right? Because it's not necessary to make the transformation. So depending on where you are in the complex plane, you're going to use different formulas for these things. Another example is if I'm interested in the way the polynomial looks near the point beta, which is very important for like edge statistics of eigenvalues for the GUE ensemble, then I would not use the outer parametrics, because I would be looking inside the disk, and I would instead put something here that involves Airy functions, right? And then I would have a formula for an, and in particular for the pi n of z, that has Airy functions in it, right? And that's exactly what's supposed to come out. That's the asymptotic behavior of the orthogonal polynomials near the edge of the spectrum. Mm-hmm.
The figure of focus then is just a 30 page.
I think so, yeah. It's not, the thing is that their paper is not about orthogonal polynomials. Their paper is about discrete Penlevet equations and their appearance in quantum gravity. And I don't know very much about either of those two things, but all I can say is if you dig through that paper, you will see in the middle of it, they mention in passing that you can get the orthogonal polynomials from this problem. They don't, that's not the point of their paper somehow, but that's the first place where it appears.
200 pages to explain.
Sorry?
Now, see if I'm clear. Do you have the program, the picture for the DN matrix?
The DN matrix.
So it's a mixture of.
This one? No.
Diagram for lens.
Oh, the lens picture. Much earlier.
Yeah.
Okay.
So the essence is the CN problem, right? And the CN problem to DN problem.
Here.
Yeah.
Yeah, this is the steepest descent step.
So you first solve the DN problem on the alpha beta interval. Just on the alpha beta interval.
Right. So after you open up this lens, right, what's left for D is just that central factor, the constant central factor. And then there's something else over here, but what's over here is one of those two factors that's exponentially decaying to the identity matrix. Likewise on the top. Yeah. So you what you've done is you in the steepest descent step you have.
Can I say it a little
Yeah.
bit and then you correct?
Of course. Yeah.
So I thought this. You first solve it on the alpha beta interval for the Riemann problem, and then you look at the corner alpha and beta and match with that with the solution there, and at last you mix them up and then evolve to get the matrix E n.
That's right.
And then that's the last step.
Mm-hmm.
This is the.
Yeah, so at this point, after you've opened this lens up, you stare at this thing and you say, I think I could solve this problem. I mean, I could throw away this jump contour. I could throw away that one, this one, that one. The only parts I should keep are this part here, and then I should keep a little bit of these four right around here, and a little bit of these four. So let me treat those things kind of separately, right? And put the pieces together at the end. It's remarkable that the Cauchy-Riemann equations that are behind the Riemann-Hilbert problem are elliptic PDEs, and the solutions of them should be very non-local functionals of the data for the problem. But somehow in these asymptotic problems, you really can kind of reduce things to solving problems as if, like, it doesn't matter what's happening inside this disk. It's not going to have an effect on the rest of the picture. I mean, it has a little bit of an effect, but it's something that's under control, is the point. Yeah, but I think that's a remarkable feature of these asymptotic problems is that in the end, after some scaling and so on, and opening the lenses and whatnot, that the problem kind of decouples into separate pieces that can be dealt with separately and then put together at the end.
And then eventually the EM matrix is a small norm.
Right. Mm-hmm.
Previous mechanism can work on it.
Right.
But that theta function, there is some long way to get to the theta function, the so-called steepest descent. Do you think you can remind us?
This function theta here?
This function theta, it comes from a long way, right?
Well, it comes. It's just the antiderivative of the equilibrium measure. It's like the probability density function. I mean, the cumulative function, probability function for the equilibrium measure.
And it has to do with G plus and G minus.
That's right.
All of them come out from the equilibrium measure.
That's correct.
Yes. Okay. Thank you very much.
Why do you
So if you know derivatives of E, then you can say something about derivatives of the polynomials. So the ones that are, so in other words, you'd like to say, so the Riemann-Hilbert problem solution has in it pi n in the one entry, pi n of z. And so, so I can write down an asymptotic formula for pi n of z. It has a big O term in it. But, one of the fundamental features in asymptotic analysis is that you can't always differentiate the big O and have it do what you expect. So you have to prove a separate theorem if you want to take derivatives. I'm just saying that it's not so hard to do that. You can differentiate the E and control it away from the jump contour and consequently get the corresponding results that way.
Where do you use Steepest?
Where in this problem did we use it?
Yeah.
It's
Right.
So it's probably maybe it's overly ambitious to call it steepest descent. It's certainly descent because what we're doing is we're moving this factor here. This factor here is something that's oscillatory on the real axis. But now it gets transported onto this curve instead. And on this curve, this quantity is exponentially small instead of oscillatory. So somehow we have descended into the valleys of the real part of the exponent. So in that way, we are doing some kind of descent, right? Now, if it were steepest, we would somehow go in the direction where that is really the steepest, these are sort of square root type branching saddle points somehow, and we would maybe want to go forever in some direction like that. But it's not so important. The important thing is that we go a little bit off the axis, and that gives us some exponential decay, which is enough. Yeah.
Is it something to do with the airy kernel that Tracy would?
Yes. So if you take the kernel K, KNXY, which it's not written here, but it's written in the slides from lecture 1 with a typo, by the way, we found out, right? So anyway, that reproducing kernel, if you take it and compute it in this region near beta over here, if you compute it in this region over here where we have the airy parametrics acting, right? Then that reproducing kernel is the airy kernel plus corrections. And if you control those corrections in the correct norm, the trace norm, etc., then you're able to make statements about the corresponding point process for eigenvalues near the spectral edge, and that's exactly this kind of airy process with the airy kernel. Mm-hmm.
So that paper was already close to Tracy Whittem's work,
right? So Tracy and Whittem did this for the Gaussian unitary ensemble, finding all these quantities without any steepest descent Riemann-Hilbert stuff. It did not exist when they did that, right? But what they did is they used asymptotics of Hermite polynomials, which are so in the case when v is x squared, the polynomials are Hermite polynomials, and they have, as it happens, an integral representation. So you don't need to use Riemann-Hilbert if you don't want. You can study them from their integral representation. If you go to x to the 4, that doesn't work anymore because the polynomials for the potential x to the 4 are not classical. They don't have an integral representation, and so there's nothing you can do. Well, I mean, there's some things. Of course, you can still use kind of weak asymptotics that come from this logarithmic potential theory that the approximation theorists have known for some time. But if you want to get this universality of like the spacing distribution in random matrix theory, that's not going to help you. And so for that, it was necessary. That's really where in 1999, these papers of Dave. Dave and Krieger-Bauer and McLaughlin and Joe and Benekides. There we go. Yeah. So those papers came online, and there they explained that you could use this Riemann-Hilbert technology to get similar formulas that one knows for the Hermite polynomials in the case of x to the 4, for instance, or whatever. Right? And that's what leads to universality in random matrix theory, the fact that you can derive the same airy kernel near this edge. All you need is this square root behavior that we were talking about. That's the thing that makes the airy functions show up there, and that's a universal feature. So that's what comes out of this work. You can't tell that without somehow having a tool for analyzing the orthogonal polynomials that's not sensitive to the existence of an integral representation that one has to regard as rather special.
I mean, it seems, is it reasonable? You are saying that forecast isn't Kitari. They use the Dave Zhao method of steepest descent to work on the
No. All I'm saying is that they were the ones to write down what is in this talk Riemann-Hilbert problem 1, which is just the Riemann-Hilbert representation of orthogonal polynomials. That's what they did. I mean, as I said, it's not even the point of their paper. It's just one small remark that sort of appears in the middle of this paper on quantum gravity. Right, and then people gradually realized that, hey, this is a useful tool. I shouldn't regard this problem as something that I can say I have solved. in terms of orthogonal polynomials. That's how it appeared in the Fokas-Itzkataya paper. Like, here's a Riemann-Hilbert problem that can be solved by orthogonal polynomials. Okay, we're done. We walk away. But then the emphasis shifted, and people realized that, wait, it's more that you should use that Riemann-Hilbert problem to find out features of the orthogonal polynomials that you can't get other ways. And that's what I'm describing in this lecture, and that's what was done in these papers of Dave, Krieger-Bauer, McLaughlin, Vanikitas, and Joe.